So now that we know about both permutations and combinations, before you answer any question from here on out, you want to always look for keywords in the problem that tell you whether or not order matters or whether or not you can tell the objects apart. Because you're going to have to make the decision, is this a permutation or is it a combination, before continuing. Okay, so let's put those skills into practice. 13A says a small club has 7 members. The club decides to appoint an executive committee consisting of 3 members having equal status. How many different executive committees can be formed? Okay, so there are 2 key words or phrases that I see here that I want to draw your attention to. The first being committee, and the second, the equal status phrase. Okay, so committee is going to always be known as a keyword for combinations. If you're on a committee, then no one is more important than the other. You all have the exact same title. So although you may be individuals, once you're on that committee, you are more important than anyone else. You're all of equal status. And really, basically what that's saying is that you can't tell you apart from anyone else on that committee. Your duties are all the same. So that is what's going to lead us to the fact that this is a combination, because of the idea of not really being able to tell these people apart based on their committee roles, at least. Okay, so we want to choose then, out of these 7 members, that's going to be our in, we want to choose 3 of them, so that's going to be our R. So we are doing a combination of 7, choose 3. So here's the point where we would go to that formula. So the formula for this is to do 7 factorial over 3 factorial and 7 minus 3 factorial, which is 7 factorial over 3 factorial, 4 factorial. So again, you can go to your calculator. I'm going to just write this out. 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 4 times 3 times 2 times 1. And I'm going to reduce. So I'm going to reduce all the 4, 3, 2, 1s at the end. The bottom 3 times 2 can reduce with that top 6, and I've reduced everything possible. Looks like we're left with 7 times 5, which is 35 different ways that this committee can be formed. Okay, what if this same club decides to elect 3 officers, a president, a secretary, and a treasurer? Assuming all 7 members are candidates for each office, but nobody can hold 2 offices, how many possible outcomes does this election have? Okay, so now we can tell the people's jobs apart, right? The president has a different job than the secretary, who has a different job than the treasurer. So titles here on this committee, or it's not a committee anymore, now it's officers. So the titles are what make this a permutation, right? We can tell them apart now by their different duties and their different titles. So this time we are going to permutate. We're going to take 7 of the original members, and we have to elect 3 of them. And what that's saying is, since no one can hold 2 offices, it means we're not having any repeats. So this is not a repeat scenario. Okay, so going to our formula, this is 7 factorial over 7 minus 3 quantity factorial. So just 7 factorial over 4 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1 on top. Just 4 times 3 times 2 times 1 on the bottom. Canceling out the 4, 3, 2, 1s, we're left with 7 times 6 times 5. So let's see, 7 times 6 times 5 is 210. So many different ways to pick 3 people if the order matters, or if you can tell them apart, than there is if you cannot tell them apart. Big difference between doing a combination and a permutation, so you can see how important it is for you to just make the correct decision up front about which one of these you're doing. Okay, next question. It says there are 8 bands who want to play at a particular Battle of the Bands concert. How many ways are there to choose 5 bands who will get to perform? Okay, so a lot of times this word choose is also an indicator of combination, as long as there's nothing else that's being talked about that would make order mattering or telling them apart. So let's see. The order doesn't seem to matter here, right? They just want to choose 5 out of these 8. So this is going to be just a combination. We're going to choose out of these 8 bands, 5 of them. So again, we can tell the bands apart, yes, but you have to be able to tell them apart and order has to matter, both of those, for it to be a permutation. So this one doesn't count because the order doesn't matter. So I'll make that note here. Okay, so we're doing an 8 choose 5 combination. I'm going to do the easier way, let's say the calculator way on this one. I'm going to say 8, and then I'm going to go into my math, over to probability, and do number 3, and then say 5. So this equals 56. Okay, that right there is the minimum amount of work that you need to show on a problem like this. You need to show me that you're doing, you decided that this was a combination and what values you chose for your in and your R. And then you're welcome to do that next part in your calculator if you so choose. If you want more partial credit options, then maybe you choose to show the formula like I did above. Okay, those are options that you can have, but this is the minimum work to show. Okay, once these 5 bands are chosen, so they've chosen the 5 bands, they have a list of 5 bands. In how many ways are there to schedule them on the festival's promotional flyer? Okay, so now we have a schedule. That's the key word that I see here. So now all of a sudden it matters who's performing first, second, third, fourth, and fifth, right? The time of day, it's going to matter. So now our order matters. So we're going to be in permutation world on this one. Notice now they've already chosen the 5 bands though. So we're down to 5 bands being our in now, and they are going to put all 5 of those in order. So we're now doing a permutation of 5 and 5. We're going to take all 5 of them and put them in order. So we know that's 5 factorial when we do that. And we've done 5 factorial a lot. That's one you'll probably start to just notice and remember. That's 120. In how many ways could a first place and a runner-up be awarded? Okay, so in this case, they definitely can tell them apart, right? First place is different than runner-up. We can tell apart. The order in which they get ranked is important. So again, we're going to be in the permutation world. This time we have 5 bands and 2 of them, so that 5 is my in and 2 is my R. We're going to take 2 of them and put them in order, first and second, and then the other ones, the ordering doesn't matter. We're not talking about those. So again, I'm going to do it in the calculator this time. I'm going to do 5 and then math, probability, this time number 2 and 2. So it looks like 20 different ways to decide on a first place and a runner-up. Notice I did that one with the formula, but there's another way that I could have thought about this one as also part B. I could have thought, okay, well, I've got 2 blanks I need to fill out. There are 5 ways to choose the winner, and after the winner is chosen, there are 4 bands left to pick the runner-up out of. Leads me to the same answer of 20. Right, so there's different work you can show on these, but either one of these would be a good amount of work to show on a problem like this. Okay, and the last question for this note sheet says, Janie has 4 different colors of bracelets, black, white, gold, and silver. She is deciding which ones to wear today. How many choices does she have? Okay, so in this one, what I notice that there are 4 different choices that need to be made. She's got a black bracelet, a white, a gold, and a silver. So I'm going to use those first letters as my labels here. And when it comes to the black bracelet, she can either choose to wear it or not to wear it, right? So it's sort of, again, a yes, no question. We've seen these a couple times before. So when it comes to every bracelet, she's got the yes, no, do I wear this or not today options. So there are 2 times 2 times 2 times 2 different ways to do this, different choices to make, which is 2 to the 4th, which is 16 choices. So again, this one is very, very similar, or another way to do it is the subset idea. Remember that if our set is, I guess I'll call this set, I'll use a lowercase little letters inside my set so that the S's don't look the same. So this is the set of black, white, gold, and silver, let's say. So it's a 4-element set. If we wanted to write down all of the subsets, how many subsets? We know that the formula for that is 2 to the power of however many elements there are, which in this case is 4. So we get that 16 choices again. Either way you look at it, anytime you have that yes, no decision to make on, but it has to be yes, no for every single level, not for just one of them, then we know it's really a subset question and we're doing 2 to the whatever power is appropriate.